Okay, so we're moving to, so we're still with exponential, but right now we're gonna kind of explore the exponential functions. How does a function look like? We did a little bit yesterday, but today we're gonna even talk about it in more details. So the generalization for an exponential relation is, we said yesterday, y equals what? Do you remember? B to the power of x, right? Where b is the base.
The base and x is the
Or what else would it have?
A number?
It is a number, but what is it from the table of value? What would represent that base?
Ratio?
The ratio, right? It represents the common ratio. Okay? If you remember from yesterday when we did the table of value, we did the ratio, it was exactly the same as the base. Okay, now as you can see right here, we have two different exponential functions. One is exponential growth, the other one is exponential decay. Right? And I told you yesterday, if you're moving from the left to the right and then it's going up, that means it's an exponential growth. If you're moving from the left to the right and then it's going down, that's an exponential decay. Okay? So you're always moving from the left to the right and then you're seeing what's happening. Now, the equation for an exponential growth is, in this case, it's y equals 2 to the power of x. So your common ratio or your base is 2. Right? However, for an exponential decay, your base is 0.5. So it's y equals 0.5 to the power of x. So guess what? That base is the one that affects your growth or decay. If it's growth or if it's decay. Okay? So when b is greater than 1, so when your base is greater than 1, the relation is growth. It's growth. Okay? So to know if it's an exponential growth or decay, you just have to look at your base. If your base is greater than 1, it's a growth. And as you can see, it moves up to the right, right? And then as you move slowly, it's growing quicker and quicker. As you move slowly to the right, it's growing quicker and quicker. We talked about that yesterday when we did the sheet of paper. Right? At first you had 2 faces, 4 faces, 8, 16, and then went to 512, and then 1,000. So it was jumping much faster as you go more and more. So we call the b, so that b value, we call it the growth factor. Okay? So as long as it's greater than 1, it's a growth. When b is between 0 and 1, the relation is decaying. Decaying means it's getting smaller. Okay? And as you can see, the graph moves down to the right. Right? It's decreasing. And we call the b a decay factor.
like 0, half, and 1.
It could be 0.5, it could be 0.6, it could be 0.7, 0.7, 2, 3, 5, 4. Okay? It could be any value as long as it's between 0 and 1. Okay? Now, the difference between the two is just one is growing because of the base is greater than 1, so it's a growth. The one that's decaying because of the value of b is between 0 and 1. Now the rest is kind of, we have similarities. So what will the x-intercept be?
Horizontal.
What will the x-intercept be? So what do you plug in for y for the x-intercept? What do you plug in for y? For an x-intercept. Yes, right? When you're looking for the x-intercept, plug 0 for y. Okay? Because remember that if I'm looking for an x-intercept, let's say, right? The value here, the value of x is whatever it is. The value of y is 0. Anytime that graph intersects the x-axis, the value of y is 0. So that's why I can always plug in 0 for y. So to find the x-intercept, let y equal to 0 and solve. So let's do that. 0 equals 2 to the power of x. Now if I want to solve for x, there is a way to do it, but for us we don't learn that way right now. I will teach it to you when you're doing the grade 12. But what values of x can you put in? Can you plug in? You can plug in negative 100 if you want, right? You can plug in 100. You can plug in whatever number, okay? Think about it this way. If the number is positive, 2 to the power of 2 is 4. 2 to the power of 6 is whatever the number is, right? 64. And if I increase the x value, the number is going to be increasing. It's never going to be 0, right? How about if I plug in negative numbers? So what do you get when you do 2 to the power of negative 2? 2 to the power of negative 2.
Oh, you come with decimal.
What do you get?
1 over 4.
1 over 4, which is 0.25. Okay? How about if you plug in 2 to the power of negative 10?
1 over 10, no.
What's 2 to the power of 10? It's a big number.
1 over
1024.
does that, eh?
What's 1 over 1024? What's 1 over 1024? Well, 1 divided by 1024.
9.7
Times 10 to the power of what?
times to the power of 10.
At the end, what does it say?
Oh, it says negative 0.4 to the power of 10. I don't know what you're asking.
New Jersey is coming.
Yeah, then 10 to the power of negative 4. Right? So that means 0.0009 blah 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 blah. Okay? So that means it's 0. Something like this. Okay?
So the number that says negative 0.4 means how many zeros are going to be there?
It means, okay.
Okay.
It means if you move that decimal, you have to move that decimal 4 times to get to the 9. Okay? So 1, 2, 3, 4. Okay? Now, that's if I put negative 10. How about if I put negative 100? Your calculator probably is going to give you something similar, about 10 to the power of negative 11 or something like that. Right? So no matter what negative number I put in, my number is going to be close to 0, but is it ever going to be exactly 0? It's never going to be exactly 0. So if you look back here, right, if I erase this, if you look here, if I actually zoom it in, okay, but I can't because this is a picture, but if I actually zoom this in, you're going to see that that graph is going to get near that y-axis, x-axis, but it's never going to touch it, right, for both of them. Right? That blue line is going to get near that x-axis, so it's going to get near 0, but it will never get to 0. And we can prove it by plugging in very big negative numbers. It's going to still be 0.00000000000 whatever 1. Okay? So it's never going to. So when we're talking about my original exponential functions with no transformations, I'm gonna say that there's no x-intercepts. Okay? No x-intercepts. Because no matter what negative number you're gonna plug in, you're gonna still get a very small number. Okay? Do you guys understand that? Okay. How about the y-intercept? How can I find the y-intercept?
Y-intercept is 0.
0 for what?
For X.
For x.
0 for x.
You plug in 0 for x, right? To find the y-intercept, plug 0 for x. So y equals 2 to the power of 0. Anything to the power of 0 equals
1.
1.
Okay.
So the y-intercept is at 1. How about for the other function, which is y equals 0.5 to the power of 0? What's my y-intercept?
1 as well?
1 as well. So as long as I don't have an initial value, okay, which means, remember yesterday I told you, you can write as y equals a b to the power of x, where this is your initial value. We're going to talk more about this later. Okay, as long as I don't have an initial value, or my initial value is 1, b to the power of x, the y-intercept for that is always going to be 1. Okay, so if I take you back here to the graph, the y-intercept is 1. The y, no matter what that base is, as long as it's only a base to the power of x, it's always gonna be intersecting at 1. Okay? Because anything to the power of 0 is 1. Okay? Are you guys okay with this? Okay? So just to recap, the difference between the two is one is a growing or a growth, the other one is a decay, right? And what is the difference is that the base is greater than 1 for the growth, and the base is between 0 and 1 for the decay. Okay? It's not negative, it's between 0 and 1. Bless you. Okay, what I would like you to do for the next unit, I would like you to do this by yourself. So what I want you to do, I want you to find the first ratio, which we already know how to do that, right? And then try to answer the questions and graph the ratio. Okay?